So now we consider the general case. So let's say I is independent set, and we say that for a vertex B in each neighbor, and outside we have a I. So some of the vertices here are neighborhood of this I. So these are somehow, none of the vertices here can be in I. So these are somehow forbidden. And let's say remaining one are free neighborhood. So, some of the vertices here could be inside of I, but all of neighbors are not inside of this green part. So we don't care whether this is in I or not. As long as it has no neighbors in I, then we consider that as a free neighborhood of B. So let's say, and we identify this free neighborhood with a graph inside. So let's say free neighborhood of B with a graph, induced graph, which is induced by the vertices which are neighbors of V and uncovered. So uncovered neighborhood vertices induces this free neighborhood B. And again, draw this independent set I according to the hardcore model with fugacity lambda, and V is a uniform random vertex. And C be the free neighborhood of B. So all of these three are random variable. And for a graph F with n most D vertices, we write P of F with the probability that this C is isomorphic to F. So this is free neighborhood of V is a random variable. So that for specific graph F, we can find this probability where C is isomorphic to this F. Then, as before, we can actually express this in terms of other parameters. Again, PV and QB are as before, the probability that it is occupied, probability that it is uncovered. And alpha of lambda is again by the same logic as before. You take the expectation of uncovered probability and you multiply lambda over 1 plus lambda. And now this expectation of V, Q. So this is actually same as this. So before we write it this way, but this is just more fancy way of writing this, but they are same. Now we can write this in terms of this. So we condition on this C. So over all F, we multiply the probability that the C is isomorphic with F, and we take the conditional probability that the V is uncovered, assuming C is isomorphic to F. And what's this? What do we have to multiply here? Assuming you have V and its neighborhood, so I is already occupied here. And in order B to, so here these vertices are never in I, so we don't care. But what happens here? So in here, these are free vertices. So I is random variable, and assume that the I here are all revealed, and here I are not revealed yet. So we fix the event that the I here are already determined, but now this part is not determined yet. But here, every vertex is here, and V is uncovered exactly when none of the vertices here are in I. And we want to measure that probability. Because everything here is fixed, then here has no influence from here. So this are what happens in here in terms of the choice of the vertices in I are independent of outside. Then none of here are chosen. That probability is exactly 1 over P C of lambda. Because here again vertices, some independent set with size 0, which is empty set, is chosen with the probability 1 to the lambda to the 0, and one vertices are chosen with the probability lambda, and two vertices that are chosen with the probability lambda square, and you add them all together, then this is what you get. And then out of that, you choose the probability that you choose empty set. So no vertices here are chosen is same as choosing empty independent set. So this is exactly this probability, this conditional probability. Then what's this? This is the let me see. This is, you can write it as an expectation over C. So C is a random variable, and over C you take the PC 1 over PC lambda. So this is equal to that. Now again we want to write this in a different way. Now out of all, as before, you choose V, and you choose its neighbor, and you choose the probability that this is covered, this is occupied. This is nothing but the measure of this Y. So this is expectation of this Y. Give me a moment. Before we have this. Oh, okay. Let's do this. Sorry. So this is actually easy that in here, because this is D-regular, every PU is counted D times. So this is nothing but the same as 1 over N, summation of PU. So you take the expected size of independent set. And this is what? You take the expectation over all V, and you take the number of uncovered, number of occupied neighbors in here. But what's the occupied neighbor? Again, if we have I and here, then these are never occupied. So it only occurs inside of C. So all the occupied neighbors of V, so all the vertices which are chosen to be in the independent set I, all the which is neighbor of V is only in C. So this can be rewritten as that you condition on all the C, and for this fixed C, you take the probability that the K of them are chosen in I. So when this is K, then this is actually K. So we condition on this first and then on the condition. So these two are equal. And how do you rewrite this? This is the probability that C is isomorphic to F. And here is nothing but just an expectation over, this is chosen at random, and you take the number of vertices in the free neighborhood which is occupied. So here, I mean, this kind of makes sense because C is determined by I outside this closed neighborhood B. Once this part is fixed, then C is determined. And after C is determined, which I's are chosen here are independent. I mean, that distribution is fixed. And that distribution is same as a hardcore model inside of C. Then what does this become? This becomes again, in graph C, we choose a independent set according to the hardcore model. So this is same as this expression, which is the average size of the independent set chosen from the hardcore model on C. So technically, I mean, we have to write, I mean, it's better to write F here because we just condition on C being F. Yep. So now what we want to do. So we have this. Okay, so this is actually this times expectation over all C. You take the P prime C lambda over P prime C PC lambda. So this expectation. So we have two, this and this. Now what we want to do? We want to take this 2, add, and then divide by 2. Then, so this is same, right? So you add these two expressions and divide by 2, then that's nothing but the alpha of lambda. So we can actually put out some constant. Then what we want to do is we consider the all distribution on this C. We want to take the, I mean, C which maximize this. When conditioning on these two are same. So that can be say rewritten this. So we want to figure out this primum. Again, we can rewrite this as a, so this is over all this distribution of C. Let's say P of F be the probability that the C is isomorphic to F. Then, how do we rewrite this? I mean, if we just forget this for a moment, then what we want to do is we want to maximize summation of PF, AF, BF. Let's just simply write A and B because I don't want to write expression every time. Let's say this is AF and BF is 1 plus lambda P prime F lambda over D times P sub F lambda. Then what we want to do is we want to maximize this subject to summation of PF is 1, summation of PF AF minus BF equals 0, which is ensuring this second one, and all of PF are non-negative. So we want to show this. And we want to find the maximum of this linear programming. How do you do this? One of the basic ways is you consider the dual. How do you take the dual? You take y1 and y2, new variable, and multiply them. And you add them. And then you want here every coefficient on you multiply that, add them, then what do you get? You get the PF y1 plus y2 AF minus BF equals y1. And for dual, we want that comparing these two, and all the, these are variable, and then all the coefficients here are, all the coefficients are at least as large as the coefficient here. Then this actually provides an upper bound, so we want to minimize that upper bound, then that's dual. So minimize y1 subject to what? If you compare the coefficient here and coefficient here, we want y1 plus y2 AF minus BF to be bigger than AF plus BF for all F, and we want YF be at least 0. Then this is a dual programming, and this minimum value is clear and upper bound on this maximum value. So what we have to do is we want to find the one value here which provides an upper bound, and then if that value is actually feasible, then it's known that that's also achieved here. So, but especially what we want to do is we want to show that this maximum is occurred when we have a complete graph, complete bipartite graph G. So in complete bipartite graph, what we have is with some computation, if the number we want is actually this. If we do plug in these two, then you get this max minimizing vector, and then you find that this is actually that y1. Then you plug in here, then the answer we get is exactly this number, which is the number we want to prove. So now we have the value which gives the number that we want. So all we have to do is whether we can check that it actually satisfies all these conditions, whether this is feasible. So that's the only thing that we need to check. So with this choice, does it satisfy? With this choice, we need to show that this holds for all f. Then with some computation, what's this? This is basically, we want to show that this holds. And this is nothing but if you take a empty graph in the triangle free case, when the free neighborhoods are actually independent set. So we want this inequality. As long as this inequality holds, then this actually holds. Then this choice becomes feasible. So this is feasible solution. So it provides an upper bound on this number. Then that provides this number, which actually yields the upper bound on here with the exact number. So now what we want to show is that for graph f, let's say, if f is one of these two, then this inequality is trivial. Let's say f is a graph with almost d vertices, then we want to show that this holds. So, this is not too difficult. You just take this partition function, and let's say Ri is the coefficient here. Then Ri is the number of independent set of size I. And if you consider the same function for empty graph, then what's this? This is nothing but just choosing I vertices from D. And now we want to compare these two. But the first one, what do we know? If we have all I plus 1 independent sets here, you put it, this is auxiliary bipartite graph, and then all I vertex independent set here, and then we add a edge between them if this is contained in here. Then every set here, every vertex here has degree I plus 1. Independent set of size I plus 1 contains, you just choose one vertex and then kick out, and this is an independent set of size I. So there are I plus 1 ways to kick out. On the other hand, each of the independent set here receive at most d minus I edges. Because if you have a independent set of size I, then there are d minus I, at most d minus I vertices outside, and you can add, some of that to get a bigger independent set. So you have this. Then by counting the number of edges in this auxiliary graph, from the left-hand side point of view, you get this much, and from right-hand side point of view, you get this much. So you have this inequality. And again, what you know is this case, this is actually an equality. So what do you get? From here, it's easy to actually get that this t actually increase faster. Then, now using that, we can prove this. For proving that, what we have to check is that this is non-negative. But we can actually write it as some expression. This is some tedious expression, so you can check it yourself. And you can check that this expression is non-negative. So we have non-negativity here, which gives us the claim. So now this claim shows that each condition on this dual programming is satisfied with this choice. So this is feasible. So this provides an upper bound on this maximum. So you prove the theorem. And with this, we know this is actually maximized when G is KDD. And you do the integral over all lambda between, say, 0 and, say, lambda prime. Then what you get is this. And this implies that P of G lambda prime is P of KDD lambda to the G over say 2D. And now you plug in lambda prime equal 1. Then what you get? You have the theorem that the G is n vertex deregular graph. Then we have the number of independencies in G is m most the number of independencies in KDD to the n over 2D. So number of independent sets in deregular graph is maximized when the graph is disjoint union of complete bipartite graph. So this concludes chapter 10. So yeah, now we end the course here. So thank you for enduring this lectures. And yeah, and I will try to return I will try to grade the homework as soon as possible and return to you. I'm sorry that it took too long time for me to grade the homework. And there are another homework 9 still left, so I wish you have a fun time with the remaining homework. Yeah, thank you for participating on this course for the semester.